So in this video, we're going to use these very nice diagrams and photographs from the online mineralogy textbook by Dexter Perkins to illustrate the concept of twinning in crystals. We'll start with this guy over here. This is an example of gypsum. And you can imagine that in this case, we have atoms, or rather molecules of hydrous calcium sulfate that are oriented in this direction, kind of paralleling that plane there. And you might have some atoms that have a structural direction that are kind of oriented in this direction. And they would be separated over here along that plane. So everything on this side of the plane, north of that plane, would be oriented this way, and then everything on the south side of that plane would be oriented like this. So the reason why these things are called twins, so these are twins of gypsum, is that they are the same composition. So it's an identical mineral on this side and this side. They're not different minerals. They're simply different crystals. And the crystals are different merely in their orientation, not in terms of their structural arrangement. The structural arrangement over here would be the same as the structural arrangement over here. The only difference is just the way they're oriented. So this orientation is just tilted in this direction here, and these are tilted in a slightly different direction there. So twins, essentially you have two crystals. Well, I was going to use the abbreviation. I use XTLSs for crystals quite a bit. So you basically have two crystals of the same composition, and they are touching one another in contact along. Did we define this yet? This is the twin plane. That's the plane of separation where the two twins come into contact. Here are another couple of examples. Over here is a photograph of orthoclase. So we have orthoclase in this top guy. Over here we have some photographs and then a diagram to the right that shows us a little bit more clearly what's going on. This is also referred to as an interpenetration twin. This is a very common kind of twin in feldspars, and it has a name. This is also called Carlsbad twinning, but it's not the only kind of twinning that can occur in feldspars. So you can see you've got a crystal over here, and then it's penetrating this other crystal over here. So same composition, they're both made of orthoclase, same mineral, but just they're oriented slightly differently. The internal atomic ordered arrangement would be the same, but their orientation with respect to one another is a little bit offset. And then we have, as our last example down here, so-called all-bite twinning. Let's rewrite that. All-bite twinning. We'll include the L when we spell that. So all-bite twinning, also sometimes called that's a Y, synthetic twinning. So polysynthetic twinning is the same as these all-bite twins. This is where we have, again, a crystal structure where things are angled off down to our left and then angled over to the right, and then down to the left, and then down to the right. Notice they're varying in thickness. It's kind of a nice way to diagram this. These two crystals, these twins here, maybe grew a little bit faster, and then maybe these grew a little bit at a slower rate, or for some reason the rate of material coming to the crystal surface was inhibited for some reason, then it grew faster again, or something happened to allow this section to grow a little bit more thickly. But again, we just have this back and forth, down to the left, down to the right, down to the left, down to the right, etc. So they're all made of plagioclase. This can occur in any of the plagioclase compositions. It does not occur in the alkali feldspar series, so you won't find orthoclase doing this. But in the plagioclase series, anything along the all-bite and orthite join can and usually will show this kind of all-bite twinning or polysynthetic twinning. In hand specimen, you'll see it here in the form of striations. These striations are not color differentiated on color. It looks like there's a little bit of a color differentiation, but these should all be exactly the same composition. And so when these twins are developed at the macro scale, where you can see them in hand specimen, they actually look like scratches that will be something that would be visible on the surface of a nice, clean, flat side of crystal. In the microscope, we'll see it as this black and white striping. So it's kind of a classic case if you're looking at a microscope you would see something where you would have bunch of white stripes running through the mineral and then alternating with black stripes. And then as you turn the stage, some of those twins will go dark and then the others will go light, and they'll alternate. One set of twins will go extinct together and the other set will also go extinct together. So that's one of the classic ways of identifying plagioclase in thin section, because the plagioclase series has this very characteristic sort of zebra striping in crossed polars. And the Carlsbad twins are a little are evident also because you'll see basically a mineral that's almost like as if it's cut in half, although it doesn't have to be cut in half. You can have one side that's much thinner than the other, but it'll have this dual feature where one side will go dark and then the other will be light, and then you turn the stage and the other side goes dark and the other goes light under cross polars. So anyway, that's the idea of twins. These are minerals that have the same composition, the same ordered internal atomic arrangement, otherwise they would not be the same mineral. So these are the same minerals, they are twins, but they're intergrown in a way that they are at a slightly different orientation.